Okay, so we looked at discharging in the previous video. Now we're going to look at charging. We're going to change something very specific about this circuit. So instead of having the resistor up on its own circuit branch, we're going to have it as right next to the capacitor, and I'll show you what I mean. So there's the battery again. We're still going to have the two-way switch in here. But like I said, we're going to have the resistor and the capacitor right next to each other. What does that mean? Well, what it means is there's going to be an effect where instead of charging this instantly because of the lack of resistance in the wire, it's going to take some time to charge. It's not going to charge straight away because the battery has still got to deliver the current or deliver the charge to the capacitor in the first place to allow it to have the charge and store it in the first place. So it's going to be limited by the resistor in this case because the current is delivering the charge. So what is different about this situation? Well, instead of discharging, when we charge the capacitor through a resistor, what will happen is instead of a decay, an exponential decay, we're going to have an exponential increase. We're going to have an exponential increase in the voltage, because eventually, see, like I said before, this is a 6-volt battery. Eventually, this is going to be charged up to about 6 volts of potential difference. It's going to take some time, though, because we've got this resistor in the way. So we know that the voltage is going to eventually get up to 6, but it's an exponential increase, because as this charges up, the current is going to be able to come less and less and less and less because there's charge in the way. Because, like we said here, is this a negative? So we're going to be ending up with this being negative. So as this becomes more negative, it's going to repel more negative charge from coming towards it. Same thing with this one. This is positive because all the electrons have been pulled towards there. Well, eventually this is going to become positive enough where it's going to pull the electrons back. So it's going to slow down the process over time. Well, what does that look like in terms of a graph? Well, the exponential increase just looks something like that. And it will exponentially increase until it reaches pretty much the value or very close to the value of the battery in this case. Well, in the previous video, we talked about that kind of magic number, that 0.37 was the amount was equal to the time taken, is the time taken to drop V0 by 0.37. Well, this time it's not a drop, it's an increase. And it's going to happen at the same rate. But instead of the magic number being 0.37, we're looking for it to decay increase. So we're looking for it to increase by 63%. Okay, to 63% of its maximum possible value. So in this case, I'm going to draw this a little bit bigger so you can see. So there's voltage, there's time, there's the exponential increase. So eventually it's going to reach V0, or V even, sorry. It's going to reach V. And in this case, the equation will change and the time constant can be used to find what it takes to get to 0.63 of its max value. So if its max value is V, then V times 0.67 or 0.67V would be maybe around here. Then the time taken is equal to RC. So you've got to be careful when you're talking, whether or not you're talking about charging or discharging, because if you're charging a capacitor, the magic number, instead of being 0.37, it's 0.67, because you're charging it to that value and the decay becomes an increase, and so it goes in opposition. So what about charge and current then? Well, the charge that we store on the capacitor will do the same thing as this. So time, charge, you're going to store charge exponentially. So over time, you're going to get that. And then eventually you'll end up with, we can say, okay, well, if that's where I want to end up, so Q, 0.67 of Q, cross, down, that is RC. Okay, distance from there to there is RC. And so in this circumstance, we've got, we can think a lot about the fact that this is very, very different. Now, what about current? Now, in current, it followed the same rules, but with this time, it's going to do something different. Think about it. What is going to be different about the current than these two? Well, when you're charging this, what's happening to the current over time? It's dying out because eventually the charge is going to have built up, so it's not going to allow the current to flow. So we go back to the original format and we say, oh, okay, it's a decay again. And so as a result, for charging, the current decays in the same way as before, and you could go back to the 0.37 of the I to get RC. And so that's a small difference that you just need to be aware of when you're looking at charging versus discharging. Discharging for current in charging for current is always the same. Voltage and charge are going to be different based on the situation that we're talking about here. Now, obviously, we can then change this to be in this position, and it's going to be discharging through the same resistor, and so we go back to our original discharge equations, which we talked about in the previous video. So we end up getting discharge when we put it back in the other position, because again, the negative charge is going to seek out the positive. Okay, in the next video, we'll start talking about energy, and we'll actually do some practice of utilizing the equations for this topic as well.